So this is part 2 of the introduction to Redox Equilibria. Here we're going to consider something called electrochemical cells. So let's think about what a cell is. A cell is a device containing 2 electrodes immersed in an electrolyte. It is used to generate current or in electrolysis. So in your traditional batteries you will have acidic or alkaline batteries, and this will be the electrolyte within the battery. An electrochemical cell is made up of 2 half cells. We're going to consider the displacement reaction that we had a look at in video 1, part 1 for the introduction. So that was between zinc and copper sulfate. If we took a piece of solid zinc and we dipped it into a solution of its ions, so a salt solution containing zinc ions, an equilibrium would be set up. So this is a piece of solid zinc. An equilibrium would be set up whereby the zinc ions would gain electrons and would form zinc, and the zinc solid would lose some electrons and would form zinc ions. So the zinc solid would be forming zinc ions in the solution, and it would leave, there would be a build-up of electrons on the piece of zinc metal, and it would happen the other way round as well. So you would have your zinc ions in the solution forming zinc solid metal. So an equilibrium would be set up whereby the zinc ions would gain electrons and would turn into zinc solid, and it would go the other way. The positive zinc ions would stay very close to the piece of zinc metal because the zinc metal would have a slightly negative charge due to the build-up of electrons when a zinc atom moves into solution to form the zinc ion. This arrangement is known as a half cell. The same would happen with copper. If a piece of copper metal were put in a beaker with a solution of copper ions, so that could be copper sulfate, an equilibrium would be established between the copper ions and the copper metal, whereby copper was losing electrons to form the ions. However, because copper is less reactive than zinc, it will do this less readily, so it will form the copper ions less readily than the zinc would, and therefore there would be a slightly less negative charge on your electrode due to the fact that slightly fewer of the copper atoms would change into copper ions. So let's consider the equilibria that's going on in each of these half cells. So you've got zinc ions in the solution, and they are gaining electrons and they are becoming zinc metal and being deposited. You have also got zinc metal giving up electrons, leaving those on the piece of metal and forming zinc ions in the solution. In the copper half cell you have the same thing going on. Copper ions in the solution gaining electrons from the piece of solid metal and forming copper, and you have copper solid giving up its electrons, and they are going to be forming copper ions in solution. This equilibria is established so that the rate of the forwards reaction equals the rate of the backwards reaction. But within each half cell, the equilibria lies slightly different depending on the metal in question. With zinc, it is more reactive, and therefore it has a greater tendency to lose the electrons, and these would be deposited on the metal, and therefore the equilibria lies slightly to the left-hand side, whereas with copper it is more to the right-hand side. These 2 half cells can be connected together. So we have the zinc on the left-hand side in a solution of its ions, and we have the copper on the right-hand side here, again in a solution of its ions. They can be connected up using an external wire. I'm placing a bulb there so you can see that there is a current flowing through the completed circuit. The circuit will obviously need to be completed between the two half cells. This is done by using something called a salt bridge. Now, the salt bridge practically would be made out of some filter paper which has been soaked in a salt solution, for example potassium nitrate. The salt solution is chosen so that it doesn't interfere or react with the contents of the beaker, which a metal wire may well do. Potassium, as you'll be aware, is high up in the reactivity series, so it's quite happy to stay as ions, and therefore it's not going to interfere with anything that's going on in either of the half cells. When this external circuit is set up, the equilibria in each of the half cells will respond by going in a particular direction of oxidation or reduction. This will depend on their relative tendencies compared to each other to either gain or lose electrons. The tendency, if you remember from the last video, the tendency to either gain or lose electrons is known as their standard electrode potential. How this is measured we'll consider in the next video. This will mean that ultimately the zinc will actually go in the direction of oxidation, as it will be losing electrons. On the other hand, on the other half cell, it will mean that the copper half cell will go in the direction of reduction, as it will be gaining electrons. To draw these cells out can be quite cumbersome if you're having to draw the beakers, so there is a cell representation to show what is actually going on within the electrochemical cell. What this is basically a shorthand to show the species and what they are being turned into, which direction their equilibria is going within the entire cell. So we take each half cell in turn. If you remember, zinc is going in the direction of oxidation, copper is going in the direction of reduction. So we start off with zinc, solid, Zn, solid. We put a line because then what we have is zinc ions formed, and the zinc ions are in a different phase to zinc solid. So phase, when we talk about phase, we're talking about like state. So we have a solid and we have aqueous here. What we then have is a double line to represent the salt bridge, and this is then followed by what's going on in the other electrode. So in the copper half cell, you've got the Cu2 plus ions. They are in aqueous. Once again, we have a different phase, so we'll have a solid line there, and it will be forming Cu solid. So this representation gives you an idea of what's going on in each of the half cells. What you can see is the species that are in the centre by the salt bridge are actually those with the highest oxidation states, both with an oxidation state of +2. To finish off, before you watch the next video, have a go at, for each of the above reactions, have a go at drawing the shorthand cell representation to show what would be happening in the electrochemical cell.